Thank you, everyone. First, I want to acknowledge the Palava people for sharing this land with us and giving us the opportunity to work and live here. Next, I really want to appreciate and share with you the visit of Steve Warren here. It's one of the first international visitors to us, or at least to me here in Australia. And welcome you visit very much and the exciting opportunity to discuss a lot of science with you, Steve. Just as a short background, Steve Warren is now an emeritus professor with the University of Washington in Seattle. His research concerns the interaction of solar radiation with snow, clouds, and sea ice, and their role for the climate. He has carried out a lot of field work, namely in the Southern Ocean, the East Antarctic Plateau, Greenland, Svalbard, Canada, Siberia, and China. He wintered in 1992 at South Pole Station, where he was the station science leader. In 1988, he began collaborating with the Australian program via Ian Ellison, who some of us still remember. Ian might be online. And he has been involved in several sea ice voyages over the years, namely also in 2012, the Cybex 2 voyage. He's a fellow of the American Meteorological Society, the American Association for the Advancement of Science, and AGU. He has also been designated a highly cited author for the Institute of Scientific Information. He has taught many courses, including on climate, atmospheric radiation, glaciology, and more recently also on scientific writing. Altogether, he has supervised 8 master students and 12 PhD students, and some of them are even here found in Tasmania. So over to you, Steve, to talk to us today on the appraisal of an geoengineering scheme for the Arctic sea ice. Thank you very much for coming.
Which microphone do I use? Middle.
This one, please. And actually, when you point, it might be better to point with the mouse because people don't see.
All right. Okay. Is this microphone loud enough?
Yeah, that's
Okay.
good, Steve. Yep.
Okay. Geoengineering, that means artificially altering the climate to compensate for global warming. So the Arctic sea ice has been alarmingly declining, and engineers think about that, thinking, well, there must be something we can do to stop it. And that's what I'll be talking about. Now, I personally have avoided getting involved in geoengineering for many years. So at the end, I'll explain how I got involved in this project. My collaborator on this is Melinda Webster. Melinda was a graduate student in oceanography at University of Washington, got her PhD some, I don't know, maybe 6 years ago, and I was a member of her committee. My own experience of sea ice is mostly in the Antarctic with the Australian expeditions, but Melinda is an expert on Arctic sea ice and has participated in several field projects. Yeah, so, she's now on the faculty of the University of Alaska. First, I just want to say this talk is not about the global engineering, which you've probably heard about, the solar radiation management, which falls into 2 categories, marine cloud brightening and stratospheric aerosol injection. And we're instead considering regional geoengineering limited to the Arctic sea ice area. And there are 2 categories of geoengineering that might be attempted. One is to increase the ice growth rate in the winter. The other is to reduce the melt rate in the summer. On the first one, the problem is, well, sea ice thickens in the winter by freezing of water to the base. And then the latent heat of freezing must be conducted upward through the ice. So the growth rate diminishes as the ice thickens. And the proposed solution would be to pump seawater from below the ice up onto the upper surface of the sea ice in the winter, so bypassing that conductivity problem, and the water would then freeze at the surface. This was written about by Desch with a large number of co-authors in 2017. They just proposed it as an idea. They have not followed up on it. They've not done any field work, any laboratory work. So nothing's really been done to pursue that. And so I'm not going to talk about that one anymore. Instead, what I'll mainly be talking about is the second one, reducing the melt rate in the summer. And the way to do that that's been proposed is to spread white powder over the ice. It's albedo. So as I say, this is the one we're critiquing because it has proceeded much further with laboratory experiments, field experiments, and substantial funding and publicity. Have any of you heard of this idea? Raise your hand if you have. Okay. Oh, wow, several of you. Okay. Then I guess it is worth critiquing. So we start out with properties of sea ice and solar radiation that are relevant to any of these geoengineering proposals. We'll start out with the types of ice, and most of these pictures at first are going to be from the Antarctic because that's where my own experience is. When the ocean water cools in the autumn to the freezing temperature, which in the Arctic is minus 1.8 degrees, then instead of further cooling, the loss of heat goes into forming ice. And first you get these small crystals called frazo crystals, and they form a slurry in the water that damps out the tiniest waves. So it appears like an oil slick, and it's called grease ice. And then the frazo crystals clump together into tiny clumps, and then into larger clumps. If there's significant wave action, these larger clumps, maybe a meter across, called pancakes, they bump into each other and raise the edges. Alternatively, if the ice is forming without wave action in calm water, then you get what's called nilus, a flat sheet of new ice forming in calm water. Within a few days after the nilus forms, it's very likely to have experienced snowfall, and thereafter the albedo really depends mostly on the snow thickness rather than the ice thickness. Nilus, yes, you can also, from a humid atmosphere onto a cold surface, you can deposit frost, and the frost tends to suck up brine from the ice, so it's very salty. Yeah, you can taste it. It's very salty, and also raises the albedo. Frost flowers can raise the albedo by 0.2 to 0.3 at ultraviolet invisible wavelengths. Then go through the winter, and by spring, this is actually from the Arctic. In the early spring, as the sun comes up, we have fairly thick ice and then a thick snow cover on the top. Then we go into the melting season, and there's quite a difference between the Arctic and Antarctic in the melting process. Antarctic sea ice melts from the bottom up because of a large heat flux from the ocean, tends to remain snow covered as the ice thins, whereas the Arctic sea ice melts mainly from the top down. So first you melt the snow. In June, the melting of the snow, then it forms ponds because the ice is impermeable in June. And so it forms ponds at low points on the ice. And then in July, we have the melting of the surface ice and the melting of ice below the ponds, causing the ponds to enlarge. And then in August, the interior of the ice warms and brine pockets enlarge and interconnect, forming vertical channels, allowing the ponds to drain, at least partially. So this is a typical view of the Arctic Ocean in summer. And there are two types of surface here. There's this white surface, which is the drained white ice. And the reason it's bright is because the surface of the ice forms a so-called surface scattering layer because the grain boundaries melt away, and it has quite a high albedo, not as high as snow, but about 0.62. And as I say, the grain boundaries melt under the influence of sunlight. Actually, it looks like coarse grained snow. You might think this is snow, but it's not. Just from the appearance, it's actually ice, which did not originate from snow. It originated by freezing of seawater. The other surface type here is the melt pond. Has an albedo fairly low, about 0.25. It's quite a bit higher though than open water, which is only 7%. And that's because the ponds are shallow, so that light penetrates through the pond and and is scattered back by the ice below the pond and contributes to the albedo. We can break the year into two seasons, the growth season and the melt season, which approximately correspond to the dark season and the bright season. So here's a table of solar radiation reaching the surface of the Arctic Ocean in watts per square meter as a function of latitude from 75 to 90. And you can see for the 6 months, October to March, there's hardly any sunlight. And in the spring and summer, April to September, 6 months, quite substantial sunlight reaching the surface, and it doesn't vary much with latitude. And that's because, well, especially in the spring, as you go north, the sun is getting lower, but also the days are getting longer, so they compensate, and you get approximately a constant function of latitude here. So that dramatic difference affects what's relevant for the mass budget. In the autumn and winter, what matters is actually the ice is growing from below. So the difference between the surface temperature and the bottom temperature and the conductivity. So the air temperature and the conductivity are what matter. In the spring and summer, what matters is the albedo. In both seasons, you also have relevance for the mass budget of ice motion and the open water fraction, because the winds and the currents cause the ice floes to break and collide, forming rafts and pressure ridges and opening leads. And the leads of open water in the summer absorb sunlight and then transfer heat to the ice base. Snow is very important. And here's a plot of the total snow depth as a function of month of the year. So we're starting out in August, and then there's this is on multi-year sea ice in the Arctic. So heavy snowfall in September and October, and then less slower accumulation through the winter, peaking in May. I guess I could show on here at about 30 centimeters, which corresponds to about 12 centimeters of liquid equivalent. And then in June, the snow melts rapidly, and by July, it's mostly gone. Now that's for multi-year sea ice. The first year sea ice accumulates less snow because it's not formed yet in September, and the snow is falling into the ocean water, cooling the ocean water. But until you've got a nice surface as a platform for the snow to accumulate on, then you don't start accumulating snow. Then we go on to, so the effective snow cover on the mass budget. In the autumn and winter, the albedo is irrelevant because there's not enough sunlight to matter. And the effective snow cover there is to insulate the surface, slowing the ice growth. And in spring, then the snow keeps the albedo high and delays the onset of melting. Okay, now to this geoengineering proposal. It's a paper that came out 4 years ago. AGU started this new journal called Earth's Future about, 10 years ago. And that's the journal that published this paper titled Increasing Arctic Sea Ice Albedo Using Localized Reversible Geoengineering. Leslie Field is the lead author, and she has a long list of co-authors that she's gotten funding for not from the government, but from private foundations and from private individuals, from crowdsourcing. They called their project ICE 9/11. At first, they've changed the name now. And the idea is to, this white powder that I mentioned actually consists of glass bubbles. They're hollow glass microspheres, HGMs. They're tiny, radius of 32 microns and a wall thickness of 1 micron. Yeah, you can see it just it's just a powder, but they're actually glass bubbles. In fact, I met Leslie Field at the AGU meeting last year, and she brought a vial of these glass bubbles and encouraged me to stick my finger into it to feel how soft and fluffy it is. So this is what they want to spread over the Arctic, or some parts of the Arctic, wherever they could make a big influence. Now that paper reported, first of all, laboratory measurements of the radiative properties of these glass bubbles. And the thickest layer they experimented with was 330 microns thick. And if you average over weight, they did measure the spectral properties, but if you average over wavelength, it comes out to average reflectance of 43%, transmittance 47%, and they add up to 90%. That means there's an absorbance of 10% in a layer that thick. Then they did experiments on bare ice of a frozen pond in Minnesota, and spreading the glass bubbles, the albedo rose from 0.25 to 0.5.
That's a silly question.
Question? Yeah.
What happens if you breathe those things in?
If you breathe them,
Yeah, it kind of sounds like if you breathe in little tiny glass bubbles.
yeah, well, I don't
So I just
know.
noticed it was in your hand, and I don't
Yeah, I
even think of like
suppose maybe-
asbestos or
Gee, maybe I did breathe.
fiberglass.
I hadn't thought of that. Maybe I did breathe some because they're so light and fluffy.
Yeah, it sounds like it'd be kind of dangerous, to be honest.
Yeah, it does sound dangerous, and that, and you know, this is not, as we admit in the paper, there are other considerations besides the one that we are addressing, which was the radiative forcing. And in fact, there are native groups in Alaska who are protesting, thinking that it's going to damage the bird life in particular that are going to be eating these glass beads.
Yeah.
And so on. So yeah, that's there's already a lot of opposition to this project.
Thank you.
Okay, then the last thing they did was climate modeling, in which they use the NCAR community Earth system model. They arbitrarily increased the albedo over all sea ice. In fact, at the time, they weren't even able to separate out the Antarctic. So they just increased the albedo by about 0.1 throughout the year and examined the climatic consequences. But those, we're not going to look at those, or we're not going to critique their climate modeling results, because what we're going to critique is their input. We think that their input radiative forcing is wrong, and so there's no point really in looking at the climatic consequences. So rather than critiquing the climate modeling, instead we ask what could be accomplished with the glass bubbles. To answer that question, we consider seasonal cycles of solar radiation, snow cover, sea ice type, and surface albedo. And we need the radiative properties of the glass bubbles. So here's what they reported in their paper. They actually did not measure them themselves. They farmed this out to a professional laboratory to get an accurate report. So you see they, okay, this is a function of wavelength. So ultraviolet, visible, near infrared, out to 1500 nanometers. And this is the albedo and transmission for 5 different thicknesses. And the thickest one has the highest albedo, and that's 331 microns, and has the lowest transmittance. And yeah, as I said, if you average that one over wavelength, you get 43, 47, and 10 for the, well, they didn't measure absorbance, but they have reflectance, transmittance, absorbance have to add up to 1. So the absorbance we infer is about 10%. Now, here's one of their figures from their promotional literature. That is that they would find young ice with it's reflecting 30%, and by putting the glass bubbles on, it would raise it to 45%. And they say the optimal season for deployment is estimated to be October and November. That's when you have young ice or even thinner grease ice. Now, I think you'll all see there's a problem with that, in that, first of all, there's hardly any radiative forcing to be obtained in October and November because there's very little sunlight. And then the snow falls and it's going to bury these glass bubbles. There is some young ice in the spring in leaves that have opened. It's about 10%, but only a small fraction of it is so young as to be snow-free. And we're going to go into detailed calculations of this later on. But our first thought was, well, where could the bubbles be most beneficial? There are three criteria for having a big effect. One, you want to put them on a low albedo surface, and then that covers a large area. And in the summer, a surface that occurs in the summer covering a large area. In summer, because then there's plenty of sunlight to reflect. So there's one surface type that satisfies those three criteria. Yeah, what is it? In the Arctic. Don't think about the Antarctic for this one.
Paul, can you repeat the question, please?
There's one surface type that satisfies these three criteria.
The melt faults?
Yeah, it's the melt ponds. However, there's a problem with melt ponds. That is that the glass bubbles will be blown by the wind over to the edge of the pond and clump there. In fact, Leslie Field, in her paper, said that that is what happened on the pond in Minnesota after the ice melted. So we are going to dismiss the melt ponds, and we're going to compute radiative forcing over all other surface types. Actually, we do calculate it for melt ponds too, if you could somehow spread the glass beads uniformly. But then in the summary, we're going to dismiss them. So we have 8 surface types that we're going to evaluate. They're nillus, thin snow on nillus, thick cold snow on thick sea ice, thick melting snow on thick ice, the drained bare ice with surface scattering layer. Number 6, the melt pond, which we're going to dismiss. And then, well, when the melt ponds freeze, then they would be a stable platform, the refrozen melt ponds in September. And then the ice that survived the summer, at first we'll get a thin snow cover in the early autumn. So that's 8 types. Then, oh, interesting. Oh, there we are. I guess I made this modification on one of the slides. Okay, so then we do the radiative transfer using a simple something called a multiple bounce model. So let's say here's your surface, the opaque surface, which is ice or snow, and then you have this layer of bubbles over it, glass bubbles. So the sunlight comes in, and then some of it's reflected. So you get a contribution to albedo there, R sub G, reflectance sub G, G for glass. And then there's some that's transmitted through the layer of, and then that gets to the surface, and some of that gets reflected back, R sub I for ice. And some of that gets through the ice, another transmittance factor, to add to the first reflectance. So we're going to get albedo as an infinite sum, because some of this first reflected light is going to get reflected back down by the glass, and some of that's going to get reflected again by the ice, and some of that is going to get transmitted. And then there's subsequent terms in the infinite series that are additional factor of R sub I and T sub G. And it's an infinite series that has a sum. Maybe you'll remember that you take 1 plus x squared plus x cubed, etc. Infinite series sums to 1 over 1 minus x for x less than 1. And x is less than 1 because all these r's and g's are less than 1. So the formula is that the reflectance of the system is the reflectance of the glass itself plus this additional term. And Now, what we're using for the radiative properties of the layer, fortunately, they have been measured and reported. Now, what I showed you before were the reflectance and transmittance, and now we put them both onto the same plot. So this is reflectance, that one's transmittance, and they were measured out to 1.5 microns. There's still solar energy out to 2.5, so we just assumed that those properties are the same as they were at 1.5 microns. Doesn't matter all that much because there's only 8% of the incident solar radiation at the surface beyond 1.5 microns, and that's under clear sky. Under cloudy sky, it's only 4%. So anyway, we made that assumption, and then adding those, subtracting from 1, so that you get a sum of 1. This is the absorptance, and you see it's about 10% on average. Now, here's the system albedo as a function of the underlying albedo. Underlying albedo from 0 to 1, system albedo from 0 to 1. Now, the black line is if you just have the bare surface, you've not put any glass bubbles over it. So the system albedo is the same as the surface albedo. And if you put a layer, look at the red line, the layer of absorbing of HGMs, hollow glass microspheres. It's raising the albedo from 0 up to 43% or so, and somewhat less, but you're raising the albedo from the black line up to the red line. But if the albedo is greater than 61%, then you're actually reducing the albedo because of the absorption within the glass bubbles. If you have a high albedo surface, then the effect of the glass is to lower the system albedo. We also have a blue line there, which is non-absorbing HGMs. If you could manufacture these glass bubbles, if you could manufacture glass bubbles in a way that there is no absorption, a different kind of glass, then they would always increase the albedo. And there would be over any surface. Of course, as you get to higher albedo surface, the effect is less. So this point where this crossover point called a break-even albedo. If you have a low albedo surface, the glass bubble will raise the albedo. If you have a high albedo surface, they will lower the albedo. And which one wins out? Well, you could also ask, what if you have a thicker layer of glass? That was 330 or 331 microns. But if you have double the layer or 3 times or 4 times, you keep increasing the layer thickness, then over a black surface, the albedo will increase and then asymptote. Or over a white surface, the albedo will decrease and then asymptote to 0.61 after you've gotten to about 6 layers of glass. Now, the albedos of the various ice types various surface types we're considering, there's albedo from 0 to 1 as a function of wavelength, ultraviolet, and then visible, and then near infrared. The darkest is leads and open water, which is just about 7% independent of wavelength, because if it's clear water, then you're not getting scattering from below, you're just getting the mirror reflection from the surface, which for diffuse radiation is about 7%. The next one is nihilist. And now you're already starting to see a decrease in albedo into the near infrared. Water and ice, or the water molecule, has absorption bands in the infrared, but not in the visible. So you're just seeing tails of the infrared absorption coming into the visible. And the reason that the albedo is low here is not because of absorption by the ice, but transmission into the water below the ice. Next is melt pond. So green, that's a melt pond, and then there's a refrozen melt pond. And those were all measured. Actually, yeah, those were measured in the Arctic. Some of these were measured in the Antarctic. This highest albedo is thick, dry, cold, pure snow, and that is very high. It's like 96% averaged over the visible and ultraviolet, and then lower in the near infrared, averaging something like 0.82. And the next one down is thin snow on sea ice. Very important one is this blue one, which is the dominant ice type in the summer, the drained melting, snow-free melting sea ice. Now this light blue one, that's kind of peculiar. That was thick melting snow. That was measured last year on the Mosaic expedition in the Arctic. It's peculiar in that it's much lower than we would expect for thick melting snow. It turns out that was measured when the ship was stuck for a while, and there was an opportunity to get out on the ice and make measurements, but pollution, soot pollution from the ship very likely lowered the albedo to an unrealistically low value. It should be up in here somewhere, just it's coarser grained than this fine grained snow. But so what we're using for our calculations is not this one. We're instead using a measurement from melting snow on Antarctic sea ice, which was measured in the year 2000 by Tom Grenfell and Rich Brandt. That Ian and Petra remember that trip. Okay, so we go on now. We have to do spectral averages. We weight those spectra by the solar spectrum as a function of wavelength. So clear sky, and these are measurements in the Arctic, and then overcast clouds. You can see it's maybe half in the visible, but it's reduced to much more than half, much lower than half out in the near infrared. And in the near infrared, in the longer wavelength parts of the near infrared, it's much, the clouds are much, are reducing. Well, what it is that clouds are like a filter. They are also made of water, whether they're water or ice, they're made of water. They have the same absorption bands as the surface ice and snow. And so they act like a filter. They filter out the near infrared and they let through the wavelengths for which the surface has high albedo. So albedo is always higher under a cloud for snow and ice surfaces. And this effect, it's in the near infrared. Okay, so here are our band albedos for the different ice types. So, you know, cold, thick snow, nillis, and so on, summertime, autumn. For snow, visible albedo, near infrared, depends on whether it's clear or cloudy, and then the broadband visible plus infrared is higher in the under cloudy sky. So we have that for all these ice types, and there's, yeah. Okay, and then we've done the spectral averaging also for the glass bubbles, and here's what they are. Visible near infrared, clear, cloudy, not much difference there between clear and cloudy, about 43, 47, and then absorption 10% for both clear and cloudy. And then we need the seasonal cycles of the different ice types. So going through the year, January to December, January through April, it's mostly sea ice with cold, thick snow cover. And then the little numbers in italics below are the uncertainties we estimate. The rest, other than the sea ice with cold, thick snow, we have nillis and 20%, and we've assigned half of it to no snow and half with cold, thin snow. Now, here, what we're doing, and these are from Melinda's expertise in really knowing the seasonal cycles of these types of Arctic ice. We're giving the benefit of the doubt to the glass bubbles. So there's the passive microwave can't tell the difference between in nillis and open water. So we're assigning it all, giving the benefit of the doubt, saying it is nillis, even though there really is some open water, some leaves. Then we go into May, and the snow is melting. So we also have sea ice with melting thick snow, and then that continues into June. And then June, July, August, we have most of the ice well, by July and August, it's free of snow. And that's when we also have the melt ponds. And then in September, half of the melt ponds are refrozen. And leads and open water open up within the, if you go to the maximum ice extent and then you ask what remains within that maximum ice extent, a lot of it's now open leads and open water. Then the freezing happens, and we have Millis forming again September, October, and we have a surviving multi-year ice that is collecting snow and finally getting thick snow again. So we have okay, and then we have the solar radiation, the seasonal cycle, and as a function of latitude and season at the top of the atmosphere. At the surface, it's about half what it is at the top of the atmosphere because the clouds get in the way. The clouds let about half of it through. So here's what we have incident at the top of the atmosphere as a function of latitude and season, and at the surface. And then here's an average for the Arctic, peaking in June. And as I said, about half at the surface. So what the clouds do, well, they reduce the transmittance to the surface, but they also reflect sunlight. So they're contributing to the albedo and hiding the surface to some extent. Cloud cover is about 80% in the summer. Albedo of Arctic stratus clouds, about 0.4, transmittance 0.5. So suppose you increase the surface albedo by 0.25. The top of atmosphere albedo will be muted. It will be only 0.1 increase. The clouds are already have a high albedo, and having this bright surface below will raise it a bit. However, the incident sunlight at the top of the atmosphere is about twice of the surface value. So radiative forcing by these glass bubbles under the cloud at the top of the atmosphere is similar to the forcing of the surface because you've got the greater solar incidence. So the way we step through the process of doing the calculation, here's just for one example, one of the surface types, which is thick melting surface ice in 1 month, in the month of June, thick melting snow on sea ice. So we have the sea ice area, the fractional, that's in millions of square kilometers. What fraction of the area is covered by this type of ice? And multiply those, you get 3.9 million square kilometers. Here's the incident flux at the top of the atmosphere, at the surface, transmittance. And then if you put the glass bubbles, because the surface has a high albedo, it's actually reducing the albedo by about 10%. And so the radiative forcing is a positive line. Positive radiative forcing means a warming. You get 25 watts per square meter over a surface of this type. But the surface of that type covers only 35% of the Arctic Ocean. So you've got over the Arctic Ocean, it's 9 watts per square meter. And then we go through the clouds, get to the top of the atmosphere, and then get the radiative forcing at the top of the atmosphere. And it's about the same, about 9 watts per square meter. And we can go on to combine with other months to get the annual average and even the global average. So now, taking this one number, radiative forcing for this type in this month, and there it is in this table, which has all the types in all the months. So for each type in each month, we have radiative forcing by adding hollow glass microspheres. So you see a lot of positives here for the snow cover. That means a warming. Over Nillis, with no snow, yes, you get a lowering out, or get a raised albedo and a cooling effect. For the melt ponds, we put an asterisk here because we're calculating it, but we're going to dismiss it in our averages. So now and when you do all of that, but ignoring the melt ponds, you come up with an annual average of positive 3.5 watts per square meter. So the result, if you put these glass bubbles every month on the entire ocean, you would get a warming rather than a cooling. So in other words, the darkening of high albedo surface wins out over the brightening of low albedo surfaces. And here are, here's a bar graph showing not all of the types that have at least 1 watt per square meter in at least 1 month to avoid clutter here. The big positive ones are sea ice with cold thick snow, sea ice with melting thick snow. Then this is the melt ponds with asters. They're the only one with a big negative forcing. In these months, April and May, you do have a negative forcing by the nihilist, but it's outweighed by the snow-covered ice. So you have to selectively cover patches of nihilist within the snow. But we're assuming you just cover everything that's there. So here's a summary. You get positive forcing, meaning a warming over sea ice with cold, thick snow, March to May, sea ice with melting thick snow, May to June, sea ice with cold, thin snow, September to October. You get near zero forcing for the melting bare sea ice in the summer because that albedo of 0.62 is very close to the break-even albedo of 0.61. Refrozen melt ponds in September, they cover a small area and there's small irradiance from sunlight, so they have near zero forcing. And then you have the cooling negative forcing from bare nihilist and from nihilist with thin snow. And then month by month, when you sum all those up, you see that there are no months with a substantial negative forcing. There are months with substantial positive forcing, and the net forcing peaks in May, 16 watts per square meter, annual average, something like 3 watts per square meter. Oh, yeah, there we are. So here's what we then said in our abstract. The net result is the opposite of what was intended. Spreading HTMs would warm the Arctic climate and speed the loss of sea ice. But then we went on to ask, well, what if you could manufacture a non-absorbing glass powder? And we say that if the HTMs are to be spread over the Arctic sea ice to raise its albedo, it would be necessary to manufacture non-absorbing HTM, avoiding any contamination during the manufacturing process. You really have to be careful about avoiding black carbon and avoid contamination by dark substances during transport and dispersal. The idea of dispersing this was from an icebreaker ship with a tall stack and spewing glass beads out to be carried by the wind out over the sea ice. But of course, the ship's exhaust is going to be carried by the wind in the same direction. So it's going to contain black carbon. So we now assume that all those problems can be overcome, and then saying, let's assume they're going to be applied once a year. What would be the time to get the biggest the benefit? You want them to be applied at a time when they will not be immediately covered by new snowfall. They should be applied during May, then they'll be effective for the 4 months, May through August, and then they'll be covered by snow. You probably have to apply this every year. And then the blue lines are what I showed you before, the blue bars, and this is what you get from the non-absorbing glass. You get the desired negative radiative forcing, both at the top of the atmosphere and at the surface. And the average for May to August would be 9 or 3 watts per square meter on an annual average. And the amount of glass that would be required is 360 megatons. So supposing you could make non-absorbing glass beads, then, oh yeah. So actually, this 3 watts per square meter, we can compare it, what you would get, 3 watts per square meter of cooling, compare it with what would result, the warming that would result by removal of all Arctic sea ice, which is 21 watts per square meter of warming. So that's what we're trying to prevent by putting the glass beads and getting 3 watts per square meter. And then you can also get what's called the radiative forcing efficiency, the radiative forcing per unit mass for these non-absorbing bubbles. So you get watts per square meter per gigaton, and then you get an efficiency. Yeah, here it is. Oh, then the global efficiency, where you spread, the Arctic is only 3% of the globe, but to compare it with the stratospheric aerosol, which is going to cover the whole globe, That efficiency has been worked out. There's a range of estimates that vary from 0.2 to 1 watts per square meter per megaton of sulfur. There's sulfur in some form, may eventually a sulfate aerosol. So that stratospheric aerosol injection turns out to have an efficiency about 1,000 to 5,000 times larger than the efficiency of these glass bubbles. Now, this is not an apples to apples comparison. It's not even an apples to oranges comparison. It's a glass to sulfur comparison. But we did include it in our paper. And the title of our paper, Melinda is the first author. The title is Regional Geoengineering Using Tiny Glass Bubbles Would Accelerate the Loss of Arctic Sea Ice. And it's in the same journal that the Field et al. Paper, and it's in the press. Now, why did we do this analysis? Was it really worth a good investment of our time? Well, I first heard about this project, ICE 911, 8 years ago from Bob Chatfield at NASA Ames in California, close to the location where Leslie Field's working at Stanford. And he asked me about it in an email, and I just quickly wrote back, I think, 3 sentences saying why I thought it was a silly idea. And but then I wasn't going to do anything more on it. But then 2 years ago, I heard from David Keith. Now, David Keith has been a leader in evaluating geoengineering proposals. I mean, already back in 1992, he wrote this article 30 years ago, A Serious Look at Geoengineering. So he's been critiquing geoengineering proposals. He's actually planning field experiments on one of them, but he's also doing quite a different project, which is removing carbon dioxide from the atmosphere. So going right to the cause of global warming, and actually has a machine that's in development, and well, it's already working, but it's being improved. Anyway, David Keith contacted me and said he thinks that ICE 911 project is overselling itself and is overfunded, and wanted a thorough study to evaluate it. So that's what we did. And besides the radiative forcing calculation that we did, there are other considerations. One is the efficacy of spreading the glass powder from an icebreaker ship, computing the plume dynamics, and then, as we've already been talking about, damage to life in the Arctic Ocean. Okay, that's all.
Thank you very much, Stephen. Are there any questions from people in the room or online? Please speak up if you're online. Phil, please.
Not so much a question, Steve, but more just to thank you for doing this very careful sort of desktop study, because you know, it's obviously a serious problem. We need to look at a portfolio of solutions, but I think it's important that rather than money coming in from investors or for crowdfunding, that these sorts of calculations are done in a holistic way first, rather than raising the money and spending it somewhat foolishly. It would be better to try and use sort of knockout criteria like you're using to come up with the the winners, and obviously in this case here the losers, because there are so many counterintuitive twists and turns in virtually all of these processes, never mind the issues of upscaling and the non-linearities. And so thank you for stepping us through that very meticulous calculations you did. So yeah, excellent.
Yeah, thank you.
Yeah, if you spread all this stuff around up in the Arctic there, at the end of the season, and it's all floating, where does it tend to end up? Is it going to accumulate massively in one area?
Can people online hear the questions?
Oh.
Yep, we can hear. Thanks.
Yeah. So yeah, where would it end up? And that we can only speculate or think about it just as much as you could think about it. We have not looked into it, but yes, it's going to get up onto shorelines. It's going, some of it, the glass bubbles will break. With shearing against each other, they'll break, they'll fall down to the bottom of the ocean. Yeah, but a lot of it we would expect eventually would end up on shorelines.
I have one question, Steve. Would those glass bubbles actually, could you conceive that they intact would be flushed down brine channels and then get into the algae or the mixed layer right underneath the ice?
Well, if they're broken, they will. As long as they're intact, then they'll tend to float.
Yes, Paul, please.
I just reiterate what Bill said. It's just your patience is incredible. You go through all this. Yeah.
Well,
Do you have another favorite one that you're going to tackle next? Like, is there another crazy idea we should be looking out for?
This is the benefit of being retired, having time to do this.
I would lose my mind.
I'm sure you're busy with all your projects, then you read a journal article and say, oh, well, that's wrong. Somebody should write a comment on this, but you don't have time yourself to write a comment, so you just pass on. But I am retired, so I do have time. And I've also commented on a couple of other things.
Yeah. My goodness.
Yeah.
Thank you.
There is a question online from Roland. Roland, if you want to unmute and ask.
Yeah, thanks. Yes, Steve, I join everybody else in applauding your efforts here. But I'm sure your brain is too valuable to be entirely devoted to whack-a-mole for strange ideas. My serious question is, in a system like this, I didn't see any consideration of feedback in terms of the if this process works and preserves the ice cover, does one need to admit that preserving ice cover increases the area that does have a high albedo?
Yeah, I think I understand your question. If the method would work, then that was actually what more than half of the original paper was about, that they arbitrarily increased the albedo and then looked at the climatic consequences both in the Arctic and in the rest of the world. That's kind of easy to do. Climate modelers, you just plug into a climate model and you get a lot of results. And and I don't even remember really what they found, but there are feedbacks, right? You increase the albedo and then the ice lasts longer, and then you've got the albedo temperature feedback. It's
interesting that in the Arctic that's a feasible proposition, since, as you explained, the ice is sort of thermal input does come from above. Presumably would be a rather lost cause in the Antarctic.
Oh.
In the fact that the ice will get melted away from below, no matter what you're doing on the top.
Right. Oh, that's a good point. Yeah. Of course, in the okay. Yeah. This proposal was only for the Arctic, but you could. I'm hoping that we will kill this proposal, so it won't be extended to the Antarctic. Now, of course, you're always fighting against global warming. I mean, even if you raise the albedo, you still got the CO2 increasing and the long wave radiation that is eventually going to melt the ice anyway. We're in big trouble, really.
Right. Thank you, Steve. While people just probably think of some more questions, I just wanted to us to appreciate also the information about the spatial and the type difference of the albedo. So it's quite something that the models are struggling, and I think it was good to be reminded of that, because often because in our other models being used here, you have one or two albedo numbers that hold up all through the year for all ice and snow terms. Last call for questions. No, thank you. So Steve will be here.
Sorry, Petra, I have a question.
Oh, yes, go ahead.
Yeah, thanks very much for the talk. I was wondering if these glass beads could get airborne and act as ice nucleating particles to change the cloud droplets into ice.
Let's see, they could, yeah, with a strong wind, you could probably lift them, but they're much larger than even than most dust particles in the atmosphere. The diameter is 64 microns, and so they would fall out pretty quickly. So I doubt that there would be an effect.
Yeah, you need a really strong wind, I guess, then. Thanks for that.
Thank you, Mark. I just want to remind people that Steve will be here for the rest of the week. So if you have any questions or want to discuss something with him, you have his email and make contact him. He's upstairs on the 3rd floor. And invite everyone to thank Steve again for this marvelous presentation. Thank you.